Good afternoon, class. Here's elementary statistics practice test number 3. Module 3, covering chapter 6 and 7. Here's chapter 6, normal probability distributions, part 2. Again, reminding you of the pledge. When we take the exam, I pledge on my honor that I will neither give nor receive unauthorized assistance, so on and so forth. And you may use formula sheet, tables, and a graphing calculator. All right, so we're going to continue. Question number 6. IQ scores are normally distributed with a mean of 100 and a standard deviation of 15. What percentage of people has an IQ score above 120? First and foremost, you want to write the given standard normal distribution. Mean mu is 100, sigma is 15. So that's the first thing. Probability of X larger than 120, and we are going to go with Z equals X minus mu over sigma. Mu and sigma we wrote it here, and now we replace the X with 120 to find the Z score for X equals 120. Results in 1.33, which means normal distribution probability of X larger than 120 is the same as standard normal distribution, SND, when Z is larger than 1.33. So probability of Z larger than 1.33, and that means you locate 1.33 and you want the area to the right of that. That is what you are looking for. So if you go with the table, you can see the answer is 0.0918, or you can go with technology, and as far as the percentage is concerned, it's 9.18%. What is the maximum IQ score for the bottom 30%? Always start with the graph. The bottom 30%, the area is 0.3. Doesn't have to be to scale. So we are looking for the Z score. From the Z, we go to X in a moment. So the bottom 30%, from the table, the Z is between these two numbers. So Z is X minus mu over sigma. If you do the cross product, you can solve for X, which is mu plus Z sigma. You have the value of mu, you have the value of sigma, and now you plug in Z between the two numbers, and minus 0.525 is in between. This is the answer. The maximum IQ score for the bottom 30% is 92.125. Now, so we have that, and if we want to go with the technology, we are going to go with the inverse norm. The area, you have to write the area on the left side, which is 0.3. You can go with mu is 100, sigma equals 15, and you get the answer. As you can see, this is, of course, a tad different because it's using a different Z value, a more precise Z value than this one. So it makes perfect sense that there will be some discrepancy. All right. Men have head breadths that are normally distributed with a mean of 6.0 and a standard deviation of 1.0 inches. If a man is randomly selected, find the probability that his head breadth is less than 6.2. So first of all, you want to write the given. It's ND normal distribution with the given information. Mu is 6. Sigma is 1 because it pertains to the entire population. It doesn't mention a specific sample size. And of course, in this case, a man N is 1. Okay. We want the probability of X less than 6.2. We use the formula Z equals X minus mu over sigma. We have the mu and sigma. What is X? 6.2. Results in 0.2. So when probability of X less than 6.2 as far as normal distribution is concerned, for the standard normal distribution, probability of Z less than 0.2. and either from technology or table. Less than 0.2, it's really a good idea to graph it. So the location of 0.2 is somewhere between 0 and 1 and closer to 0. And we are looking for this area. So we should recognize that it's more than 0.5 because each side is 0.5 and it's a little bit more than that. So what it does, it will help you have an understanding of what number is coming your way. 0.5793 is the answer. And if we change the question that instead of 1, if 100 men are randomly selected, find the probability that their head breadth mean is less than 6.2 because there is one person here. We look at that person of interest. In this case, we're going to look at the mean, so probability of X bar, okay, less than 6.2. That's what we are looking for. And we want to go to the Z, and so in this case, N is 100. Therefore, we use Z equals X bar minus mu of X bar over sigma of X bar, where mu of X bar means the mean of the sample means, mu of X bar is equal to mu. Sigma of X bar is sigma over square root of n. This is by CLT, central limit theorem. When N is large, that means larger than or equal to 30. We're going to discuss it in a moment. Or when we know we are dealing with a normal distribution, then we don't worry about the size. So we put that into this equation. In other words, X bar, it's 6.2. Mu of X bar is the same as mu 6, and sigma of X bar is sigma 1 over square root of n, square root of 100. And this is 10 division by 1 over 10, that means multiplication by 10, we get 2. So probability of X bar less than 6.2 is the same as probability of Z less than 2. So look at the 2, and we are interested in this area. And clearly, you should recognize that as, of course, less than 1, but close to 1. And if you use the table, you get 0.09772. As far as technology is concerned, if we are looking at this case, everybody, probability of X less than 6.2, the lower number, as I've mentioned before, normal CDF, they are using -1 times 10 to the power of 99. That's what this means. It's a very small number. This is the scientific notation. Again, I'm going to write this. I want to make sure everybody gets the meaning of this. When you see that, it means -1 times 10 to the power of 99. Okay, and that means basically -1 with 99 zeros in front of it. So it's a very small number. But for our practical purposes, you can even use -100 or -1000. The upper is 6.2, mu is 6, sigma is 1. If you plug in, you get this number. As you can see, this number, of course, with more decimals, if you stop at 2, becomes 3. For this case, the upper is 6.2, mu is sigma. The difference is that sigma is 1 over 100 to the power of 0.5. That means 1 over 10. And therefore, this is the answer. Take a look. If we stop at 2, we don't change it because next to it is 4. So as clearly it indicates the two numbers are extremely close. The assets in billions of dollars of the 4 wealthiest people in a particular country are given as follows: 33, 29, 16, 11. Assume that samples of size n equals to are randomly selected with replacement from this population of 4 values. So we have 4, and we're going to pick 2. For example, 33, again, because it's with replacement, that means 33 and 33, 33 and 29, 33 and 16, 33 and 11. Then we go to 29, 29 with 33, 29 with 29, 29 with 16, 29 with 11, and all the way to the end. That results in 2 to the power 4 or 16 different possible samples. After identifying the 16 or 2 to the power 4 different possible samples and finding the mean of each sample, construct the table representing the sampling distribution of the sample means. When I explain the concept. So having said that, as it was mentioned, so we have the X bar and probability of X bar. When you use 33 and 33 with itself, the probability is 1 out of 16. But when you use 33 with 29, another possibility is 29 and 33. So these two. So this is 1 out of 16, and so is this one. And you continue with that thought, you get 16. Now I'm going to write the X bar and P of X bar. Notice, for 33, there is only one outcome, so 1 out of 16. But if you're looking at 31 as the average, this number, okay, so 33 is 1 out of 16. But why is 31 2 out of 16? Because 31 is the average for 33 and 29, as well as 29 and 33. So once happens here, once happens here is 2 out of 16, and the rest follows in the same manner. So if the number is itself, it's 1 out of 16, but anything else, there are two possibilities. Okay, this is called sampling distribution of X bar. Okay, this is the value of X bar, which is numerical, and the second one represents probability, and they must add up to 1, and they do. Now, compare the mean of the population to the mean of the sampling distribution of the sample. So of course, the mean of the population, we're taking this to be the population, and mu is summation of X over N, which means at 33, 29, 16, and 11, and divide by 4. We get 22.25. So that's the average. Is very simple to evaluate. Okay, fairly straightforward. Now, what about comparing it to this, sampling the mean of a population to the mean of the sampling distribution of the sample. So how do we find the mean here? As you recall, mu is summation of X, P of X in this case would be mu of X bar is summation of X bar, P of X bar. That is the way we calculate the mean using the discrete random variable. So the product of these two plus the product of these two plus the product of these two. That's the idea. 33 times 1 over 16 plus 31 times 2 over 16, and so on and so forth, all the way to the last one, 11 times 1 over 16. They are identical. They are equal. Mu and mu of X bar are both equal to 22.25. Now here's the meaning of it. Do the sample means target the value of a population mean? In general, do sample means make good estimate of population means? Why or why not? Yes, the sample means target the value of the population. That is, the mean of the sample means the expected value of the sample mean is equal to the population mean. In other words, mu of X bar is equal to mu. That's the meaning of it. And of course, mu of X bar uses this formula to be calculated. Very straightforward. Now, I want to discuss the concept with more details and using the idea of CLT, the central limit theorem. The central limit theorem, or CLT, is a fundamental statistical concept stating that the distribution of sample means, as it was, again, going back to this concept, okay? This is the distribution of a sample means, as an example. Approaches a normal or bell-shaped curve as the sample size increases, regardless of the original population's distribution shape. So it doesn't matter what the shape is originally. If we are looking at the sampling of the sample means, and n is fairly large, the larger it gets, the closer it gets to a bell-shaped. And large, n is larger than 30. The central limit theorem. A sampling distribution of a sample means is a distribution obtained by using the means computed from random samples of a specific size taken from a population. For samples of size n larger than or equal to 30, in some cases just 30, but larger than or equal will do the job. The distribution of the sample means can be approximated reasonably well by a normal, meaning a bell-shaped distribution. The approximation becomes closer to a normal distribution as the sample size n becomes larger. Conclusion. The distribution of sample x bar will, as the sample size increases, approach a normal distribution. The mean of the sample mean is the population mean, mu of x bar equals mu. The standard deviation of the sample mean is sigma of x bar equals sigma over square root of n. So pretty straightforward, everybody. The conceptual reason. When you take a single random observation from a population, it can easily be an extreme outlier, very high or very low. However, when you average n independent observations together, the high values and low values balance each other out. As your sample size n grows larger, the sample average becomes much more stable and reliable. The probability of getting an extreme average drops drastically. The spread or standard deviation of these averages shrinks, which is why we divide by a factor of n. The population of current statistics students has ages with mean mu and standard deviation sigma. Samples of statistics students are randomly selected so that there are exactly 44 students in each sample. For each sample, the mean age is computed. What does the CLT, central limit theorem, tells us about the distribution of those mean ages? Well, reminding you of what we just did. The central limit theorem, a sampling distribution of a sample mean, is a distribution obtained by using the means computed from random samples of a specific size taken from a population. For samples of size n larger than or equal to 30, that's the case here, the distribution of a sample means can be approximated reasonably well by a normal distribution. The approximation becomes closer to a normal distribution as the sample size n becomes larger. So that's what we just discussed. So having said that, here's the conclusion. Number one, the distribution of sample x bar will, as the sample size increase, approach a normal distribution. The mean of the sample mean is the population mean, mu of x equals sigma of x bar. Mu of x bar is mu. The standard deviation sigma of x bar is sigma over square root of n. Therefore, for n being 44, which is larger than 30, a sampling distribution of the mean ages can be approximated by a normal distribution with mean mu of x bar equals mu and standard deviation sigma of x bar is sigma over square root of n or sigma over square root of 44. Again, I wanted to repeat this because it's extremely important to understand what's happening here as far as CLT is concerned. So, to recap, we have 44 students. Because this is larger than or equal to 30, mu of x bar equals mu, sigma of x bar is sigma over square root of n, which means sigma over square root of 44. That's really the answer. In a split second, we can answer it, but I wanted just to make sure that we understood what's going on. A boat capsized and sank in a lake. Based on an assumption of a mean weight of 137 pounds. The boat was rated to carry 50 passengers, so the load limit was 137 times 50 or 6850 pounds. After the boat sank, the assumed mean weight for similar boats was changed from 137 to 170 pounds. Here's the question. Assume that a similar boat is loaded with 50 passengers and assume that the weights of people are normally distributed with a mean of 174.1 pounds and a standard deviation of 35.1 pounds. Find the probability that the boat is overloaded because the 50 passengers have a mean weight greater than 137 pounds. All right, so first and foremost, what is given? We are dealing with a normal distribution. N is 50, mu is 174.1, sigma is 35.1. So first and foremost, this is what's given as we read the question. What do we want to calculate here? Probability of X bar larger than 137. So that's what we want to calculate. Because N is not 1, when N is 1, you use Z equals X minus mu over sigma. When N is any number larger than 1, Z is X bar minus mu of X bar over sigma of X bar. And again, mu of X bar is the same as mu. Sigma of X bar is sigma over square root of N. So mu of X bar, we are going to use this number. Sigma of X bar, we're going to use this number divided by square root of 50. And for X, for this one, we put 137. It gives us negative 7.474. And graphing really helps. We want the probability of Z larger than this number. I hope you recognize. If you recall, as we start from the mean, if you go 3 standard deviations to the left and right, it covers almost everything, 99.7%. Now, on the left side, this number is much smaller than negative 3. So it's a 1 or 100%. In other words, from this number to infinity, it covers everything. So it's 100% that the boat is overloaded. The boat was later rated to carry only 15 passengers, and the load limit was changed to 2550 pounds, 170 times 15. Find the probability that the boat is overloaded because the mean weight of the passengers is greater than 170, so that their total weight is greater than the maximum capacity of 2550. So we are dealing, again, we're going to write the information. We are dealing with the normal distribution. This time we are changing the N to 15. Okay. We keep the rest intact. In other words, mu and sigma are the same. Now we want probability of X bar larger than this number, 170. So we want to go with the Z. So we're going to go with this formula. Same formula. We plug in, we find the Z. Of course, we are using 170 here. So probability of Z larger than negative 0.4524. And if we were to graph it just for the sake of argument, so somewhere here is -1 to -3, so somewhere here. So you should know it's more than 50%. So we use a calculator or we use a table, and we end up with, let me erase my work, 0.6745. It's huge. It's 67.45%. So do the new ratings appear to be safe when the boat is loaded with 15 passengers? Absolutely not. No, because there's a high probability, 67.45%, of overloading. The new ratings do not appear to be safe when the boat is loaded with 15 passengers. So that's pretty straightforward. At an airport, passengers arriving at the security checkpoint have waiting times that are uniformly distributed between 0 and 10 minutes. All of the different possible waiting times are equally likely. That's the meaning of uniform distribution. Find the probability that a random is selected passenger has a waiting time of at least 7 minutes. So let's discuss the uniform distribution. It's a continuous random variable, okay? Uniform has a uniform distribution if its values are spread evenly over all over the possibilities, the graph of a uniform distribution results in rectangular shape. Over the range of, this is range. Properties of uniform distribution. Density curve, the graph of any continuous probability distribution, is called a density curve. And any density curve must satisfy the requirement that the total area under the curve is exactly 1. Because the total area under any density curve is equal to 1, there is a correspondence between area and probability. Therefore, probabilities can be found by identifying the corresponding areas in the graph using this formula for the area of a rectangle. Area is height times the width. So having said that, what is the given? The total area on the curve must be 1, and from 0 to 10, the width is 10 minutes. So this is 10 minus 0 equals 10. So it's important to understand this, okay? The height, which represents the probability, must be 1 over width, so 1 over 10. And if we look at the graph here, we go from 0 to 10, 0 to 10. And the area must be 1, so the height must be 0.1. So probability of wait time of at least 7 minutes is probability of x larger than or equal to 7. Which means between 6 and say 8, this is 7. And from 7 to 10, this is 3 times the height. So the height times the width of the shaded area. The height is fixed at 0.1, and this is from 7 to 10. 10 minus 7 is 3. Their product is 0.3 or 30%. So that's pretty straightforward, everybody. Information regarding standardized tests used for college admittance. Scores on the SAT test are normally distributed with a mean of 984 and a standard deviation of 204. Scores on the ACT test are normally distributed with a mean of 20.7 and a standard deviation of 4.3. It is assumed that the two tests measure the same aptitude, but use different scales. If a student gets a SAT score that is 65 percentile, find the actual SAT score. So what is the process here? First, let's write the given. For this one, SAT scores, the mean is 984, so mu is 984, sigma is 204. For this group, the mean mu is 20.7, and sigma is 4.3. So that's the first thing we want to write. So 65 percentile, we do the graph. So this area is 0.65. So we need to find the z-score here ultimately. So if we use the table, area to the left is 0.65, and we find the z, and from that we go to x. Again, let me just erase my work. Over here, everybody, if you solve Choose the cross product, solve for x. X is mu plus z sigma. Okay. So we can calculate the z. Okay. Well, we can pick up the z from the table or technology because it's 0.65. So z is x minus mu over sigma. X is mu plus z sigma. We have mu, which is 984. We have sigma, which is 204. We need to find the z. And to find the z, we can go with the technology inverse norm, 0.65, mu 0, sigma equals 1, and we end up with this number. So plug in everything that you have and z with that. This is the answer. And since they want a whole number, 2 next to it is 6, it goes up. So the answer is 1063. So if a student gets a SAT score of 65th percentile, the number is this. What would be the equivalent ACT score? Well, we use this, and again, we use exactly this one. So we have the same z, now we want to get to x, but in order to get to x, this time we're going to use mu equals 20.7 and sigma equals 4.3. Okay, so mu is 20.7, sigma is 4.3. We are going to plug in here, and it's 22.4. If a student gets a SAT score of 1494, find the equivalent ACT score. Well, SAT is given. Let's go find the Z score. So that's the X. The X value is 1494. We want to find the Z. And when we find the Z score, we use it for ACT. So having said that, Z is X minus mu over sigma. So X is 1494 minus mu over sigma. We are going to use mu and sigma for SAT. And that gives us 2.5. So the Z score when SAT is 1494 is 2.5. So that's the same Z score for ACT. And we're going to use this formula, this one. And of course, with mu and sigma, 20.7 plus 2.5 times 4.3, 31.45. Since they said one decimal, 31.45 changes to 31.5, and we're done. A food marketing institute found that 35% of households spend about $150 a week on groceries. Assume the population proportion is 0.35 and a simple random sample of 300 households is selected from the population. What is the probability that the sample proportion p hat of households spending about $150 a week on groceries is less than 0.38? All right, so again, we are dealing with application problem. So what is given? We're going to start with that. %35 or 0.35, 150, 300. What are those? We are dealing with a binomial distribution. Probability is 35%. N is 300 because we're dealing with proportion here. So we're dealing with BD, binomial distribution. P is 0.35. Okay, found that 35% of households, so roughly this much. And N is 300. So Q is 1 minus P. We need that is 0.65. And we want the probability of a P hat less than 0.38. What is the probability that the sample proportion P hat of household about spending about $150 a week on groceries is less than 0.38? So probability of P hat less than 0.38. So having said that, we can write the following. First and foremost, NP and NQ are larger than 10. I'm going to leave it for you to verify that. Just multiply these two and then multiply these two. Mu of p hat is p, and sigma of p hat is square root of pq over n. I hope everybody's okay with the formula. So mu of p hat is p, or 0.35. And this one, if this is 0.35, 0.35 times 0.65 divided by n, which is 300, and take a root. So we can calculate those. So we have those values. We can put this into technology such as TI calculator. We want to be, for this one to be less than 0.38. So from negative infinity to 0.38. And by the way, because it's a proportion, you can even put negative. You can even put 0 for the sake of argument. 0.38, this is mu is 0.35. And sigma is 0.027538. And it gives us the answer. We could also calculate the z as follows. This is the second method. X minus mu over sigma. So in this case, p hat minus p over sigma of p hat. And that's 0.38 minus 0.35 divided by 0.027538, resulting in this case, which means now probability of z less than this number. And again, lower, upper, mu is 0, sigma is 1. And as you can see, the answer in all cases is the same. And if you stop at 1, 2, 3, 4, let's say here, it doesn't change. So 0.8620 is the final answer. According to a survey, 10% of Americans are afraid to fly. Suppose 1,100 Americans are sampled. What is the probability percentage that 121 or more Americans in the survey are afraid to fly? Well, we are dealing with a binomial distribution. P is 10%, N is 1,100. So it's important to write the given. So having said that, we are looking at actually a few different methods where X is 121. So three methods. X is 121. P hat is X over N, which means 121 over 1,100, or 0.11. So we want probability that P hat is larger than 0.11. That's one way to write it. And to do so, we're going to say mu of P hat is P, and sigma of P hat is square root of PQ over N. This one is 0.1 or 10%. This one, obviously 0.1, 0.9. Remember, when P is 0.1, we should know Q is 0.9. This is what we get. 0.0090453. And so therefore, we are going to go with normal CDF lower, because this is larger than or equal to 0.11. Okay. If you want to graph that. Okay. And again, you don't know the answer, but it has to be 0.11 is on the right side. It has to be less than 0.5. This is, okay, this is 0.11. This is not to scale by any means. This is negative 0.1. And so you paste it, and you get 0.13446. That's what you get here. By the way, the lower is 0.11. For the upper is 1. The reason I used 1 because it's a proportion, and the maximum is 1. But over here, when you use normal CDF, you can put 1,000, so you understand what's going on. Here's method 2. Z is X minus mu over sigma, or P hat minus P over sigma of P hat. We're going to use this one. to find the z-score. Let me erase my work. So 0.11, that's the p hat, minus p 0.1, divided by sigma of p hat, 0.009043, and we get this number. So method 2, probability of z larger than 1.105547. So that's another method. Again, you can use the technology or otherwise. Method 3, we use BD, probability of x larger than or equal to 121. It means probability of x equals 121. I want to make sure we understand. This means probability of x equals 121 plus probability of x equals 122 all the way to the probability of n equals 1100. So of course, that's way too much. Now, we use the 0.5 continually for a correction factor. I can go with 121.5. Or 120.5, and I hope you see this one. The first discrete number is 121. This one is 122, and we missed the first one, so this is out. So 120.5. So we're going to put it into x equals z. Let me just erase my work. Z equals x minus mu over sigma, where x is 120.5. Mu is NP, and sigma is square root of NPQ. So mu is NP, sigma is square root of NPQ, and we use that, and I hope you see that it becomes practically the same number as this one. Doesn't matter. Standard normal distribution. Okay. So from normal distribution, binomial distribution to normal distribution to standard normal distribution. And those are the same different z-scores because we are approximating binomial distribution, and standard normal distribution. So the lower is this number, and the upper is whatever, 100, 1000, doesn't make really much of a difference. And I hope you see that when we do that, in all cases, if we stop here, the next one is 6, we take it up to 0.1345. So it's very straightforward, and I hope everybody is okay with that. Now, we are continuing with the same question. I have put the information here, part B. What is the probability percentage that 165 or more Americans in the survey are afraid to fly? Well, we want, in this case, 165. P hat is x over n, or 165 over 1100, or 0.15. Probability of a p hat larger than 0.15. That's what we want. And with that, we are going to use the z. Okay. P hat minus P over sigma of P hat. P hat is 0.15. P is 0.1. Sigma of P hat is 0.009043. And we end up with this number. Probability of P hat larger than 0.15 is probability of Z larger than that. And I hope, again, you remember that 3 standard deviations away. This is way beyond the 3 standard deviations away. So that means the number somewhere here is 5.5. We want this area, and this area really doesn't exist. It's 0. I want you to know that for all practical purposes becomes 0. So let's look at the technology. Lower is 0.15, upper is 1, or 1000 or 10,000, doesn't matter. Okay. The reason we can use 1 because this is a binomial distribution, remember, maximum probability is 1, that's why. And when you do that, you end up with this answer. Notice this answer is practically 0. I want to make sure everybody understands what this number is again. This means 1.6, let's say, times 10 to the power of minus 8. So move this to the left. by 8 decimals. So that's practically 0. Okay. All right. Let me again erase my work. What is the probability percentage that 8% or less of the American survey answered they were afraid? They were afraid to fly and rounded to 2 decimals. So same thing, probability of P hat less than or equal to 0.08. So this becomes less than or equal to 0.08. And at this point, you can go through the process or you can use technology, okay? Less than or equal to 0.08, the lower is 0 is good, or negative 10,000. Again, why 0 is good? Because this is proportion, okay? Can't be negative, but in this case, it doesn't recognize that you're doing normal CDF. Upper is 0.08, mu is 0.1, sigma is the information that we have here. Or you write it here and look at the answer. We go with the decimal, we move it to the right, and 0.0135 becomes 1.35%.